Well, once again, a casual conversational cartoon curriculum, very concise and relatively correct, as simple as possible, as soon as possible, A and P. This is Chapter 18, the second half. We've talked about formed elements. Now let's talk about hematopoiesis again, just to get the basics down. Once again, remember that to create any formed element in the blood, the process is called hematopoiesis or hemopoiesis. They mean the same thing, just British versus English kind of stuff. The location for hematopoiesis is in myeloid tissue, which is a fancy name for red bone marrow. This is primarily where all formed elements come from. The process begins with a stem cell called a hemocytoblast, which means blood cell and beginning baby building, that original stem cell. There are at least 4 different pathways that a hemocytoblast can develop. Along one pathway, it's called erythropoiesis, eventually erythrocytes are created and released into the circulating blood. Along another pathway, platelets or thrombocytes will be produced. That process would be called thrombocytopoiesis. And in the formation of the thrombocytes, the first large cell would be called a megakaryocyte, from which little bits or tabs, you might say, of cell membrane and cytoplasm are ripped off, and those released structures are called thrombocytes. Both of these things in the circulating blood, please remember, are not cells. This used to be a cell, but it lost its nucleus. This never was a cell. It's just a fragment of a cell. But the thrombocytes get into the circulating blood. Now, erythrocytes do all their work inside the circulating blood. To get out of that, they would be non-functional. The thrombocytes, again, do their basic work inside the circulating blood also, as they're part of the process of hemostasis, forming blood clots and patching damage to blood vessels. And the number of erythrocytes that are released from the myeloid tissue is the number of erythrocytes that would be found inside the circulating blood. That is, red blood cells don't come from any other source. Likewise, thrombocytes don't come from any other source. If the hemocytoblast went along a different 1 or 2 trails, it would be called leukopoiesis, and in the process, it could make leukocytes. And of course, here are the 5 basic categories of leukocytes: neutrophils, eosinophils, basophils, monocytes, and lymphocytes. These things are created in the myeloid tissue, released in the circulating blood, and unlike the other formed elements, erythrocytes and thrombocytes, these guys have the possibility or the capability of leaving the circulating blood, going into interstitial spaces, and basically seeking out targets and trouble and such. But a very unique thing that only the lymphocytes can do is to leave the circulating blood, go to lymphoid tissue, mature, and clone themselves there. So the number of erythrocytes, thrombocytes, neutrophils, eosinophils, basophils, and monocytes are fixed by what's going on inside the red bone marrow. However, the number of leukocytes can be expanded dramatically inside the lymphoid tissue. Down here, we were talking about, well, how do you get red blood cells? Well, one way that you get extra red blood cells is by the kidney prompting the production of more red blood cells. The kidney is very selfish. If it's not getting what it wants, it complains. So the kidney needs a lot of oxygen. If you happen to have hypoxia, low oxygen levels inside your blood, then your kidneys will complain by making something called EPO, erythropoietin, which sounds often a lot like erythropoiesis. So it's the hormone that promotes erythropoietin. Now, reasons why you might have hypoxia. Maybe you don't have enough red blood cells, so you can't pick up the oxygen that is there and available. Maybe there's not much oxygen that's there and available. You're living in a high altitude or someplace that just doesn't have much oxygen in the air. Or maybe you're being very, very active and you're using a lot of oxygen, doing something athletic or such. Whatever the situation, the kidneys don't like it, and so therefore they respond by making EPO, erythropoietin. The erythropoietin will stimulate red bone marrow, that's myeloid tissue, to push the production of more red blood cells. Now, it takes approximately 5 days to go from the beginning of the erythropoietic process to releasing something into the circulating blood. So 5 days right there. Once the erythrocyte is released into the circulating blood, it's not fully mature yet, so it's called a reticulocyte. They normally represent about 1% of all the circulating red blood cells, and for them to mature takes about 2 days. So you can just think about a week, 5 days, 2 days, 7 days right there from the signal being sent from the kidneys to the red bone marrow, make more red blood cells, and when you finally have mature erythrocytes in the circulating blood. Now, because the reticulocyte lost its nucleus right before it went into the circulating blood, and the erythrocyte, of course, doesn't have a nucleus, that means that this cannot reproduce itself. The production of all red blood cells must occur inside myeloid tissue, wherever it's found. And this thing right here also can't repair itself. Without a nucleus, it can't do anything to fix itself. Well, yeah. Anyway, so this thing right here has planned obsolescence. It's got about 120 days before it's been beaten up so dramatically, bouncing into the walls of the blood vessels, that the cell membrane becomes torn and tattered to the extent that it could possibly break and spill its hemoglobin. Your hypothalamus does not like spilt hemoglobin. In fact, spilt hemoglobin will cause the hypothalamus to give you a raging fever, which explains malaria's fever. So these erythrocytes, the 99% of the circulating red blood cells inside the blood vessels, have about 120 days, about 4 months of circulation before they need to be gotten rid of, before they accidentally pop. The way you get rid of these things is you mug them. In the liver and the spleen, there are macrophages that are sitting there waiting for an old red blood cell to come by. In the sinusoids of these two areas right here, there are fixed macrophages. In the liver, they're called Kupffer cells, that are waiting for an old red blood cell to come by. If a new red blood cell comes by, they ignore it. If an old red blood cell comes by, they recognize the torn, tattered appearance, texture of the surface of the red blood cell, and they will attack it. When they attack it, they destroy the red blood cell, and then the liver will begin to process the hemoglobin. It'll split the heme from the globin. The globin is just a polypeptide, so it'll be broken down to amino acids, and the amino acids will be distributed into the plasma and circulate as if they were nutrients. The heme, however, is made up of an iron atom and something called bilirubin. And the iron is toxic if it's free in large amounts. So the iron is going to be picked up and carried by something like an alpha or beta globulin, and it'll be returned back to the liver or the spleen or the bone marrow, where it can be reprocessed. But the bilirubin's the cute stuff right here. Bilirubin has a yellowish color. If it builds up inside your bloodstream, you get a yellowish tint to the blood, and that explains jaundice in some ways, in which the liver is not doing its job well. The bilirubin builds up and isn't eliminated the way it's supposed to be. Now, the way it's supposed to be eliminated is by adding it to bile. The bile then goes down the common bile duct, eventually, into the lumen of the small intestine. There it mixes with the food. Now, the bilirubin has a greenish, yellowish color to the thing. Yellowish. And the yellowish color mixes with food material, which is kind of a pasty, gray-white taupe color. And so therefore, that material, that chyme inside the small intestine, might be slightly yellowish. If it doesn't get changed, it comes out yellowish. However, there are bacteria inside the large intestine that can convert that yellowish pigment into a brownish pigment. So the brownish color of feces indicates the presence of the bacteria in the large intestines and the presence of bilirubin coming from the liver. Not having the color of the feces brown may imply that something's wrong with the bacteria population or something's wrong with the liver. So there's many ways in which this coloration and eventually that coloration might be a diagnostic tool. Good place to start.